turn it for you?
Huh? All right, if you have any questions or anything, I'll be happy to answer those. But okay, so yeah, final exam is next week. It'll be right here in this classroom. We'll try to get started close to 6:30. You'll have just a little under 3 hours, like 2 hours and 50 minutes to take it, and should be plenty of time. Your grade report just tells you exactly what you need on the final to get whatever grade you want. Okay, so if it says you need a 93% to get an A, then it means you need a 93% to get an A. Don't if you get a 92%, please don't send me an email asking me to bump up your grade. Okay, that's kind of rude. So, because you know exactly what's expected or required of you. So this is, I think I've been very fair. I adjusted the quizzes so they're all worth out of 29, so you can get a small bonus there just to help. And if you get them all right on the final, you'll get 105. So. Alright, it's going to be all multiple choice, about 55-ish questions, and I don't know,
How many questions were on the first midterm?
35, something like that. Okay. Yeah.
How much of the final exam will be the new material and how much will be the?
I'd say like 90%. So 90% will be from after the midterm. Okay, so very strong, heavy focus on chapter 7 and on. I'll go through kind of the stuff that you should study. Okay. All right.
Sorry, one last question. Will we know our score before we get our grades?
So you will get your final, so I will send out one more email, okay, with your final exam grade, but that's also your final grade, okay, so I guess when you get that, that's your final grade, okay? So if there's mistakes in your grade report, let me know right away, because after I final grades, or file the final grades, not willing to mess around and change things up. Okay, so if there's a mistake, I'll happily correct that. But you have a week to let me know. Okay.
Are you passing off the second for the quiz, last quiz?
Oh yeah. I have quiz 2 to return. Yes. That is a good point. Is it okay if I pass these out, or do you okay, all right, so just I guess don't judge other students or anything like that. Okay. All right, then let me talk about what will be on the final. Okay, so 55 questions, and the first couple pages will be a little bit more conceptual, okay? So you'll have about 10 questions, so that's a good portion, okay, that are conceptual. So these really get into the nitpicky details of hypothesis testing and inference, okay? so this is not a question that's on the final, but okay, I'll take the uncollected quizzes here. Okay, so but something along these lines. This is not going to be on the final, but is rejecting the null hypothesis the same thing as accepting the alternative? Okay. So yes or no. What do you think?
Makes sense. If you say alternative is greater than,
The
it might be.
answer is yes. If you've rejected the null, it is accepting the alternative. Okay, so
Is that the same thing as saying that the alternative is true?
yes. So rejecting the null would be the same thing as saying that the alternative HA is true. Yeah, that's or asserting. Okay, so rejecting the null hypothesis is asserting that the alternative is true. Okay. Yes.
What if it's directional, right? What if you say it's greater than something, but then
Okay.
we reject
yeah.
null,
So
but
if
turns
you
out to be
rejected the null,
Right.
then you are asserting the alternative. Okay. So even in a directional case, in the directional case, you won't. I know what you're getting at. In that situation, you would not reject the null. Raul, I have a grade report right here for you. So, I wanna get that. Okay, so just looking around, it seemed like some of you may have gotten this question wrong. Okay, so there are there's like 10 of these type of questions. Okay, so well, I guess I'll spend some review time today going into some of these things without explicitly giving away the questions on the final exam. Okay, but so there's stuff like this. Yeah.
Well, I remember when we first talked about the null hypothesis and accepting it. we
Yeah.
said
Okay,
there
so
was
what
a-
you're used to saying, okay, is but not rejecting the null is not the same thing as accepting the null. Okay, so this is true. Okay, not rejecting the null is not the same thing as accepting the null. Okay, but rejecting the null is the same thing as accepting the alternative. Okay, so yeah, these are. Okay, so we'll spend some time going over this. Okay. All right, so you got about 10 questions there, okay? And then I've got about 5 questions going over which is the appropriate statistical test, okay? So choose appropriate statistical test. So I will also spend some time going over this. You know, do you use the chi-squared test, goodness of fit, or do you use the ANOVA or t-test for paired data, or Wilcoxon and Whitney, or things like that. Okay, so we'll have 5 questions on that. And then there's like 30 something questions, just a bunch of statistical tests. Okay, so 30 plus questions. involve things like, you know, so we've covered a bunch, right? The t-test for independent samples, t-test for paired samples, the ANOVA and goodness of fit, chi-square goodness of fit, chi-square test for independence. So you have to know all of those tests, and for each of them, okay, you might be asked, what are the hypotheses? Okay, and each test has a different set of hypotheses, right? So we can go over this, but like the t-test for independent data is mu1 minus mu2 equals 0 for the null, and the alternative is mu1 minus mu2 is either greater than or less than or something not equal to 0. Whereas if it was hypothesis test for paired data, it's mu of the difference equals 0 versus mu of the difference doesn't equal 0. So it's different. So make sure you know all of the differences there. Okay. The hypotheses, you know, actually doing the test. So getting your test statistic and p-value. And then maybe interpretation of the conclusion. Interpretation of the conclusion, or what else do we have? I don't know. Whatever else might go with hypothesis testing. Okay. And then there's probably going to be like 5 or so just miscellaneous grab bag questions. Okay. So in terms of stuff from before the midterm, there won't be any calculation stuff. Okay, so I won't have you calculate like probability trees or anything like that. All right. Questions on this? Yeah.
How about from before, we're gonna have like normal approximation questions?
Yeah, no calculation stuff
Mm.
from before prior to the midterm. Okay. So.
Well, how about the programming? Any
Yeah,
question?
nothing. No R questions. No. Yeah. Okay. All right. Well, maybe I'll start with this, choosing the appropriate statistical test, and then we'll get into this, and then we'll cover, I guess, a review of all the test methods. Alright, so picking the appropriate test. Okay, so first we look at our response data. Centered here. Okay, and we could have response or a categorical response? Numeric response and categorical response. Okay, and then we look at our explanatory variable. Okay, so if we have a numeric response, and let's say we have a explanatory variable is numeric. So we have a numeric response and a numeric explanatory variable. What is the statistical method that we would use there?
T-test.
Correlation or regression, we just covered this last week, right? So if we have two numeric variables, so numeric response and a numeric explanatory variable, we will do correlation or regression. That is from chapter 12. So correlation, regression, and then you have the test for significant correlation is etc. Okay, so that's a numeric explanatory variable and a numeric response will be correlation or regression data. Okay. If you have a categorical explanatory variable, then we have several situations to deal with. Okay, the categorical explanatory variable. Then there's several tests that we can use. Okay, so maybe we'll start off with the easy case. If you have, let's say, the explanatory variable that's categorical, let's say has 3 or more categories. What would we use there? ANOVA. So that's chapter 11. So 3 or more. I mean, technically you could do ANOVA with just two categorical. Okay. Explanatory variable, then if we have only two categories, then there's still several tests that we can use. So if we have 2 categories, then this is where we enter t-test area. Okay, so if we have paired data, or like before and after, or any type of situation like that, we would use the paired t-test. And if we have independence data, then we have to see if it seems like it's comes from a normal distribution, or if the data itself doesn't come from normal distribution. The central limit theorem could be applied. Okay, so we basically have either if the central limit theorem holds, then just independent t-test. And if the CLT does not hold, we'll do the Wilcoxon-Mann-Whitney test. That would be our one non-parametric test that we went through. So paired t-test is chapter 8. I think 8.1 and 8.2. Just do chapter 8. Okay. This is chapter 7, and this is also chapter 7. Okay, categorical response. So down here. Okay, if we have no explanatory variable, okay? Actually, we have a situation where we have a no explanatory variable here. But anyway, no explanatory variable for categorical response, then we are either going to be dealing with confidence interval for P, the proportion, okay, or chi-squared goodness of fit. Okay. Chi-squared confidence interval for P generally when there's only two categories, and chi-squared goodness of fit generally when you have more than two. But technically, goodness of fit could also apply with just two categories as well. Okay. And if we have categorical explanatory variable, then it will be chi-squared test for independence. And the one thing that we did not learn, so I'm just going to do a dotted line, you don't need to know, but if you want to know, is if you have a numeric explanatory variable, then this will be a logistic regression. Okay, but we did not learn that, so you don't need to know. Okay, so just everything other than this. Okay, yeah. Chi-squared goodness of fit, this is when you have no explanatory variable, but you have like the proportions in mind. Okay, so we'll say expected proportions, but there's no explanatory variable. You're just saying, do the expected proportions fit? Okay. So a lot of these things, these tests, also depend on how your data is recorded. Okay. So something like someone's weight, we might think of that as a numeric variable. And generally it is a numeric variable, weight. However, it could be turned into a categorical variable. So we could just classify weight as I guess normal weights, normal BMI, overweight BMI, obese BMI, or I don't know what else there might be. But you know, we could turn weight into a categorical variable by kind of setting these cutoffs, right? Same thing with age. Age is generally numeric, but we could turn it into categorical. We could say, I don't know, under 18, you know, from, or 18 to whatever, 55, and then 55 plus, or something like that. That would turn into a categorical variable. So, a lot of these, which test you use depends on how the data is recorded. So, you might have to watch out for that as well. Okay. Right. Other questions on this?
Yes.
Yes. Okay.
I see numeric, I see categorical, right?
Yeah.
Like you said, numerical can be categorical if we divide them into categories. I also see both has categorical explanatory variable. How are they different under numeric and under categorical? Can you give an example?
Yeah, so if your response, if you keep your response as a numeric thing and you've got a categorical explanatory variable, then you're gonna do one of these. Like
I guess,
yeah.
what is a categorical explanatory variable under
Categorical explanatory variable will be things like, so examples where you would use this would be, we measured, I don't know, the heights of people, you know, is there a difference in height between men and women? Okay, so men and women would be the categorical explanatory variable, and the response would be the height.
Oh, well.
Or, you know, is there a difference in the weight gain of the lambs or whatever on different diets? Okay, so we have the response being the weight gain, that's a numeric response, but the explanatory variable is the diet, and that's categorical. We had diet 1, diet 2, diet 3. Okay. Here, we'll try a few examples. These are from chapter 13. There's a small section that go over, you know, which test should you use here? Okay. On page 563, if you want to look in your book, I will read these out loud to you also, and you can think of the response. Don't shout it out, and then we'll just because other students might take a little bit longer than you do in coming up with the answer. All right, so this is 13.2.1 on page 563. Says, researchers conducted a randomized, double-blind clinical trial in which some patients with schizophrenia were given the drug clozapine and others were given something else, a different drug. Okay. After 1 year, 61 out of 163 patients in the, we'll call it drug 1 group, showed clinically important improvement in symptoms, compared to 51 out of 159 in the drug 2 group. Right? What is the appropriate test that we would use there? Okay, don't shout it out. Think about it for a second. Okay, so what is the test that we would use there? Now you can say that.
Chi-square test for independence.
Chi-square test for independence, exactly. Okay, so the response is, did they show improvement in symptoms? Okay, so they either did yes, they showed improvement, or no, they did not. That's the response. And then the explanatory variable is which drug did they receive? Did they receive clozapine, drug 1, or haloperidol, drug 2? How do you pronounce those things? I don't know. So, huh? Haloperidol. Okay. See, I'm not familiar with these things. I should. I'm teaching this class for life sciences, but I'm not familiar with this stuff very well. Okay. So drug 1 or drug 2, that's your explanatory variable. And you want to see if there's a relationship, if there's a difference in the amount of improvement. So that would be chi-square test for independence. Yes.
So does it count? It doesn't count as like a before or after type thing?
It would count as a before or after
What I was initially
our results were, if we were using some kind of numeric thing there, okay? So how do we show, the question is, how did they record whether or not there was improvement? There's probably some kind of scale, right? There's probably a checklist. It's like, do you show this symptoms, or like, I don't know. But somebody, okay, at the end of the day, somebody turned all of that into did they show improvement or did they not show improvement? So the way they recorded the data that we are analyzing is categorical. Improvement, yes. Improvement, no. Okay? You're right. In gathering the data, there was probably something, okay? We don't know the details of how the schizophrenia is rated, okay? Right? That's it. Did someone show improvement or not? It's a slightly subjective thing that an expert has to do, okay? And yeah, I don't know. We don't know those details, but we do know it was either yes, they showed improvement, or no. So our response is categorical.
Okay, so isn't that based on numeric data though?
Yeah, everything could be considered based on numeric data because, well, but in essence, we are categorizing things, okay? And so the data that we have to deal with is categorical, right? Even something like hair color is technically numeric, kind of, okay? It's like, what is the concentration of melanin in your whatever, I don't know, whatever it is that causes your hair color to be lighter or dark, or things like that, right? So technically, you know, I would say I have black hair, but then, I don't know, there's probably a bunch of different people who would say they have black hair, but then if you stick all of our heads together, it's not all exactly the same color and things like that, and, you know, how many categories are you gonna make, right? So, things that we might say are categorical may not be, I don't know, so yeah, if you're recording your data as categorical, then it's categorical, even if there's a numeric thing underlying it, okay? So, that's, otherwise we'd have too many numbers. Okay, so the next one, 13.2.3. It says, a biologist collected data on the height measured in inches and peak expiratory flow, a measure of how much air a person can expire, measured in liters per minute for 10 different women, and here are the data. So you have height measured in inches, peak expiratory flow measured in liters per minute, and they want to know, is there a relationship between the two variables? Okay, so think about it for a second, don't shout out the answer, but what is the appropriate statistical method or test that we would do to see if there's a relationship? Okay, what is this? Correlation. We have two numeric variables. Height measured in inches, so that's a numeric variable. Peak expiratory flow, also measured in a numeric variable, liters per minute. And so if you have two numeric variables, that will be correlation. Okay. All right. 13.2.5. It says a geneticist self-pollinated pink-flowered snapdragon plants and produced 97 progeny with the following colors: 22 red plants, 52 pink plants, and 23 white plants. The purpose of this experiment was to investigate a genetic model which states that the probabilities of red, pink, and white are 0.25, 0.5, and 0.25 respectively. Alright, so think about this for a second. Shout out to the internet. Alright, so what is the method that we would use there? Yeah, chi-squared goodness of fit. So we have a categorical response, which is the color of the plant, pink, white, or red. And there's no explanatory variable other than the genetic model, and we just want to know if these proportions fit our data, 0.25, 0.5, 0.25. Okay. Okay, so 13.2.7 says the effect of diet on heart disease has been widely studied. As part of this general area of investigation, researchers were interested in the short-term effect of diet and endothelial function, such as the effect of triglyceride level. Okay, to study this, they designed an experiment in which 20 healthy subjects were given in random order a high-fat breakfast and a low-fat breakfast at 8 a.m. following a 12-hour fast on days 1 week apart from each other. Serum triglyceride levels were measured on each subject before each breakfast and again 4 hours after each breakfast. If you had access to all the measurements collected in this experiment, how would you analyze the data? Oh, this is you know what? I don't know if we've learned this actually. Well, we can talk about this. Okay. High fat, low fat. Oh, okay. So this one's a little bit more complicated, but let's just hear your answers here. Yeah, so this one, it's like a paired t-test, but it gets a little bit more complicated. It would actually be a form of ANOVA, okay? But it gets, it would be that block ANOVA design or the two-way factorial ANOVA design that we didn't really discuss in detail, so I will make sure there's no, well, I'm writing the test, so I won't put anything like that, okay? Paired data could work, just to see if there's a before and after effect, but you're also interested in the high-fat, low-fat, so there's a before and after that goes into it, and then a high-fat, low-fat, so because of that thing, it gets into like a two-way or a randomized block ANOVA, so sorry, I shouldn't have read that one. Okay. 13.2.8, it says biologists were interested in the distribution of trees in a wooded area. They intend to use the number of trees per 100 square meter plot as their unit of measurement. So I guess they go 10 by 10 meters and they count how many trees are in there. They were concerned that the shape of the plots might affect the data collection. So to investigate that possibility, they counted the number of trees in the square plots, round plots, and rectangular plots. Okay, so I guess they tried out different types, and they measured all of these things. So they counted the number of trees, and they're comparing whether they were square plots, round plots, or rectangular plots. They want to know if there's a relationship. Okay, so what do we do there? What analysis method?
ANOVA?
That would be ANOVA. That would be ANOVA. We have 3 categories, and our response is numeric. It's the count of trees in the spot. Okay, so I think for the most part, it should not be too terrible. Okay, just read the problems, and you should get an idea of. Well, you'll have to pick out which test to do. Okay. Is that all right? So let's talk about walk a fine balance of giving you good information talk about hypotheses. Okay. Alright, so we have a null hypothesis. And an alternative hypothesis. The null hypotheses will always have an equal sign, okay? And then the alternative will either be directional or non-directional. A lot of tests, you can only have non-directional alternatives, okay? So, non-directional alternatives non-directional alternatives only for, okay, we have ANOVA with degrees of freedom 2 or more. So that would be basically three or more categories. I should say numerator degree of freedom. 3 or more categories. Chi-squared test for independence, or no, chi-squared test both for a goodness of fit and independence, okay, with degrees of freedom 2 or more. And what else? Non-directional, so I think that's it, okay, I think those are, so chi-squared test for ANOVA, if you have more than 2 degrees of freedom, or two degrees of freedom or more, you're only allowed non-directional alternatives. Okay? And that's because if you say it's less than for this category, you don't know where the surplus is going to go. Okay. When you have a directional alternative, so let's say we have a t-test, independent data. The null hypothesis says mu1 minus mu2 equals 0. The alternative says mu1 minus mu2 is greater than 0. What do you have to do when you have a directional alternative?
Times 2.
Well, the first thing is you got to check directionality. Okay, so check to see if your data matches the directionality of the alternative. So what does it mean for your data to match the directionality of the alternative? In this case, it means x bar 1 should be greater or less than x bar 2, according to our alternative. It should be greater, okay? Should be greater x bar 2, okay? If it's not, if x bar 1 is actually less than x bar 2, then what happens?
Can't reject them all.
Yeah, it means we're not going to reject the null, okay? It means we do not have any evidence to support the alternative, okay? So, let me write that on there. So if x bar 1 is less than x bar 2, then we will not reject the null, okay? We have no evidence to support the alternative, okay? And what does that tell us about our p-value?
It's greater than 150.
Yeah, whatever it is, it's going to be over 50%. Okay. It's greater than 50%. Technically, if you were to go through the entire test, okay, you would take your tail area and subtract that from 1, and that would be your p-value. Okay, so technically, it would be your p-value is equal to 1 minus the tail area, right? Okay, but if the data does match the directionality, so if x1 is greater than x2, so data matches directionality, then what do? Then we carry out the test. And look up the test statistic in the reference table. To get tail area. Right? And so for a t-test, the tail area equals the p-value. Okay? But other tests, that might mean you have to take the tail areas and divide by 2, depending on the table. So chi-squared test, and for ANOVA, the F table, but we hardly use the F table. So, but like for the chi-squared test, you would have to take your tail probabilities and divide by 2. The Wilcoxon-Mann-Whitney test, also, I think you take your tail probabilities and divide by 2. Okay, I think those tables say they're for non-directional alternatives. So check with the table. You may or may not have to divide by 2. So I think check table. Okay. You may have to. Sorry that it's so squeaky. another thing about hypothesis tests, alright, is that we always assume that the null hypothesis is true. The data that we observe is never used to, quote, prove that the null hypothesis is true. So the data we observe is never used to prove that the null hypothesis is true. The data can only be used to cause us to reject the null hypothesis. Okay, so the data will either lead us to reject the null hypothesis, okay, which rejecting the null hypothesis is equivalent, okay, to accepting the alternative. Alright, so the data will lead us to reject the null hypothesis, okay, or to the data will be insufficient for us to reject the null. Okay, so if it's insufficient to reject the null, that does not prove the null is true. It just means it's not enough to reject the null. Is not enough to reject the null or accept the alternative, okay? Again, this does not prove, the data doesn't prove that the alternative is false either. It just means, in this scenario, it's just not enough for us to make these conclusive statements. Okay. All right. Okay. So what is meaning of a p-value? All right. A p-value tells us the probability probability of observing data like ours for something more extreme if the null hypothesis were true. a large p-value tells us that our data has a high probability of occurring even when the null hypothesis is true. Meanwhile, a small p-value tells us that our data is unlikely to occur or if the null hypothesis are true. Okay. So, you should know the different hypotheses that you would use for the different tests. And so know what, you know, if you get a p-value of 0.09, what does that mean in the context of this type of hypothesis test? Question? Okay, you're all done.
So just leave it here.
Okay. Yeah.
Do you want this?
No, you can keep that. Alright.
Thank
Thanks.
you.
Okay, so if you get a p-value of say 0.09, you know what that means. So for example, if we did a t-test for paired data, p-value equal to 0.09 means, what does that mean? It means if the true difference between group 1, group 2, or true difference between like before and after is 0, then there is a 0.09 probability thing about this test is that it's multiple choice. So you can read through the answers and pick the one that sounds correct or sounds most correct to you. Okay? And that also reduces my stress because students will write something that's like kind of right but not really, and then I have to decide, do you know what you're talking about or not? So with multiple choice, it'll be you picked the right one or you didn't. Whether you knew what you were doing or not, it's easier that way. So, well anyway, so you should know. Well, are there questions on this interpretation, this sentence, anything? Okay, so know what this, know what a p-value is, okay, and know what it is in the context of the problems there. Okay. All right. Is this all right? So far, so good. Okay. Know the difference between type 1 and type 2 error in alpha, beta, and power. Type 1 error and type 2 error. Okay, so type 2 error, the probability type 1 is equal to alpha probability of type 2 is beta. Type 1 error is rejecting the null. When the null is true. Okay. Type 2 error, do not reject or did not reject the null. When null is false. Okay. Generally, increasing alpha will decrease beta. And decreasing alpha will increase beta. The only way around this would be to increase sample size. Okay. Increasing sample size will allow us to reduce beta without having to increase alpha. Okay, so when do we pick a large or small alpha? large alpha, if type 2 error is worse than the type 1 error. Okay, because increasing alpha decreases beta. So if the type 2 error is worse, we want to reduce that at the expense of increasing alpha.
Can you give an example of that?
Okay, so alright. Okay, so let's say you go to the doctor, right? And you say, you know what, I have this tumor thing. I've got this something on my skin, alright? I wanna make sure it's nothing to worry about. So they scrape some skin off, okay, and they put it in a test. Okay. So what is worse? Is it worse to say you have no cancer when in fact you do? Or is it worse to say you might have cancer when in fact you don't? Type 1. Okay, well, we haven't said which one's type 1 and which one's type 2 yet, okay? So which one's worse?
It's worse to say you don't have cancer when you do.
Yeah, it's worse to say you don't have cancer when you do. Okay, so would that be a type 2 error or a type 1 error?
1.
Okay, so, alright, let's think about this. Alright, we took some skin or whatever it was. I don't know what they do in a biopsy, okay? They take some cells and they look at them, alright? We always use the data we collect to support the null or support the alternative.
Support the alternative.
Support the alternative. So in that case, our null would be no cancer, and the alternative would be cancer, alright? So if we say you don't have cancer when in fact you do, and that's worse, okay? So this is the worst error, is to say no cancer when reality is cancer, okay? That's the worst error. So saying no cancer would be rejecting or not rejecting the null. That would be not rejecting the null, right? When null is false. So this is a type 2 error. Okay? That's the worst error, is to say no cancer when the reality is cancer. Versus what? Okay.
I'm sorry, how did you decide that no cancer was a null and not false?
Because we are using, right? So what's this? In general, do you go through life assuming everybody has cancer until we test them and say you don't have cancer, or we assume somebody has no cancer until something indicates that they do? So we assume that the null is true until we have evidence otherwise. So that's why we assume people have no cancer until there's something that tells us that they do. So that's why it's out. Alright, so in this case, this is worse, so that's a type 2 error, and because the type 2 error is worse than the type 1, we would prefer a large alpha, okay? And so that's why they'll say, oh, you know what, come in for more tests, right? They usually, or like for tuberculosis, TB, they do that skin test thing, and then if they're like, oh, something happened, then they come in for more tests, all right? Because you could just have an allergic reaction to whatever that skin test thing is, but if they just want to make sure, so they do additional tests, because it's worse to say oh, you don't have tuberculosis when you actually do or something. Okay, so that's worse. So in that case, we have a sensitive test, large F. So we have more false positives than as a precaution. Okay. Or like I don't know, going to the airport, right? You're like so, like anything, your whatever, your belt buckle can set off the metal detector, okay? Because they've decided it is far worse to let someone onto the airplane that might be dangerous than inconveniencing everyone else who is not. Okay. On the other hand, we prefer small alpha. If type 1 error is worse than type 2 error. So these would be, in general, situations where it's better to presume innocence than guilt. So criminal cases, or I don't know, other type of things. Okay. I'm trying to think. What else do we need? Yeah.
Sorry, so the null for the innocence and guilt, the null would be innocence.
Right. Yeah, what do you assume is true until the evidence says otherwise? So in that case, in a criminal case, you assume they're innocent until proven guilty. So your null is innocent and your alternative